So in general, if you want to find the area between two curves and you can tell the endpoints either because they've been given to you or because you can tell where the two curves intersect, we can integrate the integral from left to right, the top curve minus the bottom curve. That's if we want to draw in our imaginary rectangles, infinitely many, infinitely thin rectangles vertically, which so far is the only way we've ever tried it. We'll talk about how we could do it differently in a little while. So this sort of technique works for those two problems we just did, whether you write it as two separate integrals or not. This is what we're doing. We're integrating from left to right, top minus bottom. Notice that this function, now it's time, this function, this expression, will only work if the same curve is the top curve and the same curve is the bottom curve all the way along. If you ever find that the curve changes, which curve is on top or which curve is on bottom changes, you're going to have to separate into separate integrals. That's what happens here in example 4. It's the third example on this page, but it's example 4 in your textbook. I have this region, the whole region is called R, and I know my curves. This is y equals square root of x up here. And this is y equals x minus 2, this line here. And I want to find the area in the first quadrant. So I know that x equals 0, the y-axis, the vertical axis, and the horizontal axis are part of my boundary because they're the first quadrant boundaries. So I also have this boundary here. So the question is, could I try to write an integral using that form that we just have in the box right above? Is there a curve that is always the top limit? And it turns out there is. Y equals square root of x. If you wanted to imagine, I strongly suggest you sometimes imagine drawing in these vertically oriented, imagine they're infinitely thin rectangles, right? Does the top of every rectangle I draw hit the curve y equals square root of x? Yes, it does. So that's good. So in this problem, the top curve is square root of x. The problem is when I try to figure out the bottom curve. Notice that these rectangles are all standing on the x-axis, which is the bottom curve in this case, has the equation y equals 0. In this section, the bottom of my green rectangles touch this curve, y equals x minus 2. I'm not going to be able to write one integral like this because I don't always have the same bottom curve. So one technique is to notice where did the rectangles change from touching y equals 0 as their bottom to touching y equals x minus 2 as their bottom. You can kind of tell in this picture because your book has set this up for you to notice. It happens right here. That's the place where x equals 2 because that's where this lower boundary line, y equals x minus 2, sort of crashes into the x-axis. So I'm going to write two separate integrals. Watch this. All right, so remember this picture. Between x equals 0 and x equals 2, I had square root of x on top and y equals 0 as the bottom. And then in this section, I have y equals square root of x on top and y equals x minus 2 on the bottom. Watch how that shows up when I write the integral. All right, so here's my integral. Since there were two different combinations of top curve and bottom curve, I'm going to write two separate integrals. I'm going to integrate from 0 to 2, square root of x minus 0, so top minus bottom. And then I'm going to add together because it's like I've broken up the picture into two parts. I'm going to find the two areas separately. I'm going to need to add the areas back together. That's why this is addition. And then for the second part of the picture, the part that was called B, The limits are x equals 2 to x equals 4. I have the same top curve, but I have a different bottom curve. Make sure that second curve, the bottom curve, goes in parentheses so the distribution is subtracted. So once you write this, we're really just finding antiderivatives. Again, practicing what we used in chapter 6. So the good news is this minus 0 doesn't have any effect. So I'm going to take the antiderivative of square root of x is 2/3 x to the 3/2. I'm going to evaluate that from 0 to 2. The antiderivative here of x squared, square root of x, is again 2/3 x to the 3/2 minus the antiderivative of x is x squared over 2. The antiderivative of, so I've distributed that subtraction, and the antiderivative of 2 is 2. So if you were taking the AP test and you wrote this, that would almost certainly be worth 2 points, for sure, at least one. Probably 2 points. If you found correct antiderivatives, another point. And if you get at least this far, which is evaluating those antiderivatives at the appropriate limits, that's worth the 3rd point. If for some reason this were a multiple choice question and you needed to simplify, you would need to carry on with those steps at the end. All right, so at the top of this page, we have another way that we could think about integrating to find the area between curves. If instead of integrating from left to right of top minus bottom, if we lined our rectangles up to lie down horizontally and we had infinitely many horizontal rectangles, we would write our integration a different way. We would have, oh good, so we're gonna go back to this picture. What if instead of drawing my rectangles vertically, I drew them horizontally? Right, there's nothing special about how you orient your rectangles. We're just trying to add up the areas of a bunch of rectangles. And the cool thing is, for this picture at least, if I draw my rectangles horizontally, there's only one left curve, there's only one right curve. This curve, y equals square root of x, always makes the left-hand boundary of those green stripes I'm drawing. And y equals x minus 2 always makes the right-hand boundary. So I can actually write one integral if I want. One thing that's tricky is if you think about finding the height of that rectangle, although now it's horizontally oriented, it really kind of looks like the length of the rectangle. Right, this is a horizontal line segment. If you needed to find the length of a horizontal line segment, you would take the x-coordinate that's further right, and you would subtract the x-coordinate that's further left. So that's what we're going to write here, and you see it at the top of the next page. We're going to integrate from bottom to top of right minus left. So if we're going to do that, that means if bottom and top are going to be my integration limits, those are y values. It means I'm going to have to write my integral in terms of y. But I'm going to write it in terms of y, and I need an expression for the x coordinate because that's what I want to subtract to figure out the distance across a horizontal line segment. So that's the big deal here, is I'm going to have to take that equation, y equals square root of x. I'm going to have to solve it for x. So what's happening to x right now? X is having its square root taken. So to undo that, I'm going to square both sides, and I'm going to get y squared equals x. Similarly, I'm going to have to take that equation, y equals x minus 2, and I'm going to have to isolate the x. So y plus 2 equals x. So now I'm going to be able to write my integral. Watch this. Here's my new integral. I'm integrating from bottom to top. So the lowest y in the picture was 0. The highest y is 2. And I'm going to have my right-hand curve subtracting my subtracting my left-hand curve. Here's my right-hand curve, y plus 2. And I'm going to subtract the left-hand curve, which we said was always y squared. So if you had seen this problem on the AP test, it would be your choice if you wanted to integrate with respect to x or with respect to y. The advantage to integrating with respect to y, you can write it in one integral. The advantage to integrating with respect to x, you don't have to resolve those little equations for x. So totally your choice. You'll notice that we're going to get the same answer either way. So I'm going to find an antiderivative for y plus 2 minus y squared and evaluate that from 0 to 2. If you wrote that, I'm sure that's worth at least 2 points on the AP test. You can leave your answer once you get here, as long as you remember these big brackets. And then you could simplify your answer just to prove that we get the same answer as when we integrated with respect to x.